Hello everyone. Today we're taking a look at Unit 1, Lesson 1. This whole unit is going to look at the idea of linear systems. So in our grade 9 review, we looked at linear equations, and all a linear system is basically two lines or two linear equations on a graph. And when we're trying to solve that system, we're trying to determine where do those two lines cross. Okay, so we often call that in mathematics the point of intersection. So today we're going to look at some different options in terms of the number of solutions we can have for a linear system. So we're going to solve a system of two linear equations, and we're going to want to try to find the point of intersection. And this will often be referred to as just the POI for short. Okay, and this is the point where two lines cross. And we basically have three scenarios of the way in which lines can cross. So we can have one solution, which essentially means we're going to have one POI. So in this case, if we have one solution, we're going to have something that probably looks something like this, where we have one line, and they're only going to cross at this one point. Okay, so you can see here that these lines are moving in opposite directions. There is only one solution to this linear system because there's only one point where those two lines cross. So we can say that the POI is the only point that lies on both lines and satisfies both equations. So what I mean by that is we can see by looking at the graph that the point of intersection is on both of the lines because it's exactly where those two lines cross. And if we were to look at the equation that it relates to each of those graphs, that point would also work in both of those equations, which we'll take a look at later. So when we were learning about lines, we talked about two characteristics of lines that we are always kind of looking for in math, and those are our slopes and our y-intercepts. So when we have one solution, you should see, like I said, that these lines will be moving in opposite directions. So we can see that we're going to have different slopes. If we then take a look at what the y-intercepts look like, in this particular example I drew here, we can see that the y-intercepts are different. But if the point of intersection happens to land right on the y-intercept, then they could possibly have the same y-intercept. So when there's one solution, we're just going to say that the y-intercept can be the same or different. So there's situations where the y-intercept would be different, and there's situations where the y-intercept might be the same. And so we'll continue to look at that. The next case, in terms of linear system solving, there is a possibility that there's no solution or that there's no point of intersection. So think about what that might look like if we're talking about a linear system where they never cross each other. We've seen this in mathematics, and we've talked about, and it's actually the definition of parallel lines. So two lines that never cross are parallel lines. So the linear system might look something like that. So parallel lines have no point of intersection. Okay, they never cross. So we can, by looking at this, we can see hopefully that in this case the slopes are the same, right? The lines are running in the same direction and they're running at the exact same steepness. That's why they never cross. So they're going to have the same slopes. But one is always going to be higher than the other. They're never going to cross each other. So their y-intercepts are going to be different all the time. Y-intercepts, different. Okay, and finally there's a possibility of infinite solutions or infinite points of intersection. I'll put with an S because you're going to have infinite. And you might thinking, well, what will this look like if we're going to have infinite solutions, meaning that there's going to be a ton of points that intersect or that are the same. And what that is, and when you draw this on your notes, if you can try to maybe draw it thick enough so you can see what I'm saying here, it's basically going to be one line, okay, and then you're going to have another line lying on top of it. So it's two of the same lines essentially. I'll just try to draw it a little thicker. So this is the idea that two lines that lie on top of each other will intersect at every point. Okay, so they're going to have, all the points are going to be points of intersection because they lay right on top of each other. So in this case, you're going to have the same slopes, right? Because they're just a line on top of it. It's just the exact same line with the exact same equation. So same slopes and the same y-intercept. So let's take a look at some linear systems and see if we can determine how many solutions we'll have. So determine the number of solutions for each pair of lines. So we'll take a look at their slope, we'll take a look at their y-intercept, and then based on the note we just took above, we'll determine how many solutions it will have. So let's first remember, what does the equation of a line look like, so we can take a look at where's my slope, where's my y-intercept. So all of these lines are going to be in the form y equals mx plus b. Okay, and remember that m is our slope and b is our y-intercept. So when we look at these equations, we can identify our slopes and our y-intercept. And what does that mean in terms of the number of solutions? Okay, so for our first equation here, our slope is the m value, so it's that value in front of our x. So it looks like the slope for the first equation is -1/2. That's the slope for the second one as well. So in this case, they have the same slopes. And then if we look at our y-intercepts, so we have a y-intercept of 5, and we have a y-intercept of -4. So that tells me that we have different, obviously, y-intercepts. Okay, so if we look at that note above, when we have the same slopes, but we have different y-intercepts, that means we only have, we have no solution, we have no solution, right? These lines must be parallel because the slopes are the same. So we're going to say, therefore, parallel lines. So no solutions. Let's take a look at the next one. Our slopes here, we have 3 and -3. So this time we have different slopes. And if we look at our y-intercepts, we have 7 and we have 7. So these are same y-intercept. So again, if we look up at our note above, in which case do we have different slopes but the same y-intercept? That is only when there is one solution. So we can say, therefore, there's one solution for this linear system. Okay, we'll continue on. If we look at the next one, hopefully we can logically think through this one, but these equations are exactly the same. So there is no slope here, but we can, it's implied that there's a 1 here in front of my x. So we have same slope. Okay, and our y-intercept is -8 and -8. So same y-intercept. Okay, so we can say, based on the fact that it's the same slope, it's the same y-intercept, therefore it's the same line. So we have infinite solutions. Okay, I'm going to go ahead and pause the video here. See if you can determine how many solutions there will be for this last example. Okay, so hopefully by looking at the slopes and the y-intercepts, you were able to determine that there would be one solution. The next part of the note is we're going to determine the solution for an actual system now. So it's great we can identify if we have 0, 1, or infinite solutions, but let's actually try to figure out, well, what is that solution? So we will break down what our slope and our y-intercept is, and then we will put those on the graph and see if we can then check our answer algebraically. So if we look at our first equation, we'll say that this is equation 1. Okay, we can figure out what's our slope, right? So there's nothing in front of my x here but a negative, so it's implied that it's a -1. So we'll say that our slope is a -1 over 1, because we always want to have that rise in that run, and our y-intercept is a +7. Okay, so whenever we're graphing, I'm just going to make a note here again so we remember, you always want to start by plotting your y-intercept and then use slope to plot the next consecutive points. So if we started our y-intercept is 7, I'm going to go along my y-axis up 7, so 1, 2, 3, 4, 5, 6, 7 will be somewhere here, and then my slope has is a -1 over 1, so I'm going to go down 1 over 1, down 1 over 1, down 1 over 1. Okay, and then I am going to draw a line, try to make my line as straight as possible. All right, and we can label this as y equals -x plus 7, so we know which equation. We'll take a look at the second equation, equation 2, and this time we have a slope of 1/2 and a y-intercept of -5. So we're going to plot that y-intercept first. 1, 2, 3, 4, 5. Okay, and we have a slope of up 1 over 2. So we're going to go up 1 over 2, up 1 over 2, up 1 over 2, and one more time just so we can really see where that point of intersection is. And then we will connect those dots. Always good to extend that line, the length of the graph, in case you don't quite hit your point of intersection in the few points that you plotted, then you want to extend it so you're sure to hit it. So this was the equation y equals 1/2 x minus 5. And we can see that we have a point of intersection where those two lines cross right here. So we can even label that point of intersection. So it looks like that point of intersection is at 1, 2, 3, 4, 5, 6, 7, 8, and down 1. So 8, -1. So when we're discussing linear systems, that would be the solution to our system. Okay, we have two lines. They cross at a point of intersection with one solution, and that solution is 8, -1. We should now check that answer to make sure it works in both equations, because remember above we said that a solution will be on both of the graphs and it will also satisfy both equations. So we're going to perform a left side, right side check. With that point, 8, -1. And this is to check your answer algebraically. That's why we're doing that, is because we just want to make sure that we graphed okay, everything about our graph is accurate, and if we did so, then it should work out in each of the equations. So if we look at equation 1, right, and I'm going to draw a left side, right side t-chart here. The left side of equation 1 is just y, and the right side is a -x plus 7. So anywhere I see an x, I'm going to plug in 8, and anywhere I see a y, I'm going to plug in a -1. All right? So instead of a y here, I'm going to put a -1, and instead of an x on my left, I'm going to put in an 8. So on the left side, that -1 just continues down, and we have a -8 plus 7 is going to equal a -1. So you can see that those two values are the same. They equal each other. So for equation 1, the left side does equal the right side. So you can say, yep, that checks out. And we'll go ahead and try with equation 2. So we'll set up a left side, right side t-table. The left side of my equation is y, and the right side of my equation is 1/2 x minus 5. And then we'll just substitute in. So for y, we're going to substitute in a -1. And for x, we're substituting in 8. Okay, so 1/2 times 8 is going to be 4 minus 5. And again, equals -1. So that point of intersection also works on equation 2. So again, we can say the left side does equal the right side. It does check out. So we can just wrap everything up by saying, therefore, the point of intersection is 8, -1. It checked out algebraically, so we conclude that that is in fact accurate. Let's take a look at this second linear system here. So again, we're going to identify our slope and our y-intercept. So for this first equation, our slope is going to be a -2/1, and our y-intercept is a -5. So we always want to start by plotting our y-intercept. So our y-intercept is -5, 1, 2, 3, 4, 5. And our slope is down 2 over 1, down 2 over 1. We'll go ahead and try to draw as straight of a line as we can. Okay, and then we're going to label that line y equals -2x minus 5. Okay, for the second equation, this looks a little different. It doesn't have the mx plus v, but when we have the y equals 5, what that really means is that all values of y are 5, but x can be any value. But x can be any value. So what I mean by that is, let's just throw any value out there for x. Let's say that x is 1. Well, y is going to be 5. 1, 2, 3, 4. Okay, and let's say that x is -7. 1, 2, 3, 4, 5, 6, 7. Okay, y is still going to be 5. So no matter what x value we have, y is 5. So you can hopefully see that that is going to create a horizontal line. So y equals 5, if we remember from last year, is simply a horizontal line. Okay, if we look at our linear system, or these two lines, we can see that we have a point of intersection at 1, 2, 3, 4, 5, so at -5, 5. Okay, and then of course, we should check our point of intersection, so we're going to check -5, 5 in each of our equations. So we'll check it in equation 1. We'll set up that left side, right side check. The left side of my equation is y, and the right side of my equation was -2x minus 5. So anywhere I see an x, I'm going to plug in -5. Anywhere I see a y, I'm going to plug in a +5. So my left side of my equation, y is 5, and the right side of my equation, I'm going to substitute a -5 in for x. So we're going to have -2 times -5 is a +10, and that's going to simplify to 5. So you can see the left side is 5, the right side is 5, so therefore left side equals the right side. It's like check. So let's make sure that that point of intersection also satisfies the second equation. So we'll do a left side, right side. So the left side is just equals 5, and the right side is 5. So our y value is 5, so not much really to check there. You can see that that does work out. So therefore, the left side equals the right side. So that checks out as well. So one more time, we can conclude that therefore the point of intersection is -5, 5. Okay, we're gonna look at linear systems of a word problem now and see if we can use what we've learned today to find the solution to this word problem. So Tin Box Car Rental rents cars for a one-time fee of $80 plus 15 cents per kilometer. Car Love will rent you a car for $50 plus 20 cents per kilometer. Determine the equations that represent the cost to rent from each company. Okay, so we have a couple variables in play here. I'm going to use my highlighter here. Okay, so we're determining the equation of the cost, so we need to figure out the cost, but the cost is going to be determined by a couple things. It's going to be determined by that one-time fee, plus it's going to be determined by how far you drive. So we need to have some variables that are going to represent that information for us. So let's let C represent the cost of the rental. And remember that cost of the rental includes the one-time fee of $80 or $50, depending which company you go with. But then it also includes, there's going to be some charge for how many kilometers you drive. So we don't know how many kilometers you have driven or how many kilometers this customer is going to drive. So we have to have a variable for that as well. So let's let K represent the distance driven in kilometers. All right, and now we need an equation for each of these. So let's first look at Tin Box Car Rental. It says there's going to be a one-time fee of $80 plus 15 cents per kilometer. So let's first look at Tin Box. So we're trying to figure out what's the cost to rent from Tin Box. So we know we have a variable for that. It's going to be cost equals, and then it's going to be our one-time fee plus the fee per kilometer. So I'm wanting this to look like the equation of a line we've gotten used to. So we're going to say it's going to be 15 cents per kilometer. So 0.15 times that K, right? That's going to be the kilometers driven, plus a one-time fee, which in this case is 80. If we take a look at Car Love is going to charge $50 plus the 20 cents per kilometer. So Car Love is going to have a cost of 20 cents per kilometer, so 0.20 times K plus that $50 one-time fee. Okay, so we've essentially created a linear system here. We have two equations of lines. We are supposed to determine the point of intersection of both of these, okay? So determine the equation that represents the cost to rent from each company. We've done that. Part B is asking us to determine the point of intersection by graphing both equations, okay? Now, it's a little harder to determine our slope because we have it as a decimal. So instead what we're going to do is we're going to do a table of values. So let's first do a table of values for Tin Box, because we can always graph from our table of values, and we know that we're going to have some kilometers driven, okay, that's going to essentially represent our x variable, and that's going to relate to some cost, okay. So it says here for a tip, your x-axis distance should increase by every 100 kilometers. So let's use that information to help us with our table of values, okay? It's saying that our x-axis or our x scale should increase by 100 kilometers. So we'll start at 0, and we'll do, let's say, 3 additional points, okay? So we'll determine what is the value of, what is the cost to us if we drive 0 kilometers, 100 kilometers, or if we drive 200 or 300 kilometers, okay? So if we plug in 0 into our Tin Box equation, so we're going to take this and we're going to plug into this equation up here. What do we get when we plug those values in for K? All right, so if I plug in 0 for K, I'm going to end up with 80, because 0 times 0.15 is 0, plus 80 will be 80, okay? If I were to plug in 100, hopefully we can see that we would get 95, and just continuing on, if I plug in 200, I'm going to get 110. And if I plug in 300, I'm going to get 125. All right, let's take a look at what car love looks like. So again, there's going to be kilometers and there's going to be a cost. And we'll take a look at our cost for 0, 100, 200, and 300. So if I plug in 0 into this equation now to determine my cost, if I plug in 0, 0.20 times 0 is 0, plus 50 will be 50. Okay, and then you can work through finding these other ones. If I plug in 100, you're going to get 70. 200, you're going to get 90. Hopefully we see what the change is here, what the cost is going up by each time, right? Looks like we're going from 50 to 70, 70 to 90, so we're going up by 20 each time. So it's going to be 110 for 300 kilometers. So let's graph the points we have so far on our table of values and go from there. Okay, so it gave us the tip that our x-axis, which is our distance, should go up by 100. So I'm just going to spread my 100 out a little bit. I'm going to do 100 every other line. And I think that, that should be good enough for now. We'll just go up to 600. Okay, and we'll just make sure we label that axis as our distance in kilometers. And then along our y-axis, we might as well label what we're doing there. So on our y-axis, we're going to have our cost, which is in dollars. And we can look at kind of the values we have there to gauge what we can do along the y-axis here. It looks like we're getting up into the hundreds. So I'm going to let every line represent $10. But I'm just going to write, every 50. So I'll say 10, 20, 30, 40, $50. I go 60, 70, 80, 90, 100, and so on. So we should be able to squeeze in just about 200. Yeah, 200. Okay, so if we plot that first line, for a tin box, when we drive 0 kilometers, it's still going to cost us $80. We're going to have a point there. At 100, it's going to cost us $95. At 200, we're at $110. And at 300, we are at $125. So somewhere like there. Okay, so we can connect those dots, and we'll see where we're at. If we switch over to car love and we try to graph those points we have, well, at $0, it's going to cost us at 0 kilometers rather, it's going to cost us $50. At 100 kilometers, we're looking at $70. 200 is 90, and 300 is 110. So hopefully you can see by looking at the graph and even by looking at our table of values that when Tin Box goes 200 kilometers, it costs $110, but that's the same cost as when Car Love goes 300. So those two lines haven't crossed yet, though they haven't met yet. There hasn't been a point where the kilometers is the same and the cost is the same to make that point of intersection. So this point here where the cost is the same but the kilometers is different tells us that we need more points. So we're going to continue on until we find a point that's going to be the same. Okay, so I'm just going to, on my tin box, I'm going to keep going up by 100, and we'll go up to, let's go up to 700. Hopefully we've noticed a pattern here that for tin box, it looks like my cost is going up by 15 each time. So 80 to 95 is 15, 15. So I'm just going to keep going up by 15. So from 125 for 400 kilometers, it's going to go up by 15. So let's say it's 140. And then it goes up by 15 more. And then another 15. And then another 15 on top of that. Okay, and let's check out over here for Car Love. It looks like the rate of change is 20 each time. So 50 to 70 is 20. So we'll keep going up by 20s for each 100 kilometers. So 300 kilometers is $110. 400, we're going to go up by 20, so it's going to be 130. and then 150, and then 170. And finally at 700 is going to be 190. Okay, so hopefully we can see a point on here where the kilometers is the same and the cost is the same. Now that looks like somewhere right here. So tin box at 600 kilometers is going to be $170, and the same is true for Karlov. So we'll plot those points and see if that works out to be true. So for tin box, we were up to 300 kilometers. At 400 kilometers, we're going to be at $140. Be right there. Oops. That's a highlighter. I need a marker. Okay. And then at 500, we're at 155. And at 600, we are at 170. Okay, so I'll just extend those lines, and we'll do the same thing with Karlov. So we are at 300 kilometers. To go to 400 kilometers, we're going to be at $130. And then at 500 kilometers, we're going to be at 150. And then at 600, we're at 170. Okay, so we can see that that point of intersection, again, is right there, just like it was on the table of values. And it was at 600 kilometers and $170. Okay, we should make sure that we label our graphs. So this was Karlov in green, and we had tin box in blue. And then let's just answer that last question there. What does the point of intersection represent? Well, hopefully we can see that it represents, we're looking at the relationship here between cost and kilometers. So it basically tells us that at 600 kilometers, it's going to cost the same, $170 to rent from both companies. If you drive less than 600 kilometers, you know, which company should you use? If you drive more than 600 kilometers, which company should you use? So let's first state that at 600 kilometers, it will cost the same, which in this case is $170, to rent from both companies. All right, if you were to drive less than 600, so let's say if you drive less than 600 kilometers, which car company should you use? Well, if we look at the lines here, hopefully we can see that if we were to drive less than 600, our cost is going to be lower if we go with this Karlov company. Okay, so if you drive less than 600 kilometers, you're going to want to use Karlov. Okay, if you were to drive more than 600 kilometers, then go ahead and use tin box, because you can see that once you get past 600 kilometers, the green line is going to be then go above that blue line, right? So tin box is actually going to be less if you drive more than 600 kilometers. Okay, that is it for today's lesson.